Tonight, we embark on a journey, a quiet, contemplative drift through the profound mysteries that lie at the very edge of our understanding, venturing out to what NASA has observed at the precipice of everything we know. We'll explore the universe with instruments of unparalleled precision, marveling at the cosmic tapestry they reveal, from the birthplaces of stars to the ancient echoes of creation itself. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our exploration begins with a truly remarkable feat of human ingenuity, an instrument that has redefined our perception of the cosmos, a space telescope that stands as a testament to decades of relentless effort and audacious scientific ambition. This magnificent observatory, far surpassing its predecessors in power and sensitivity, was conceived with a singular, breathtaking mission to peer into the deepest corners of space and time, to witness the universe as it was in its infancy, to observe the very first flickers of light from the earliest stars and galaxies. This colossal marvel of engineering, so immense that it had to be meticulously folded into a compact, origami-like configuration to fit within the confines of its launch vehicle, represents a pinnacle of precision. Its delicate sensors demand an environment of extreme cold, maintained at temperatures barely above absolute zero, preventing its own intrinsic heat radiation from interfering with the faint, ancient light it seeks to capture. The journey to its operational state was long and arduous, spanning decades, and incurring a cost that ascended to $10 billion. Its intricate design incorporated hundreds of potential points of failure, each a challenge to overcome, a testament to the perseverance of countless engineers and scientists. Yet, against all odds, it has arrived, fully functional, poised to unlock secrets that have eluded humanity for eons. Its mission parameters are nothing short of revolutionary. It will meticulously scrutinize distant planetary systems, searching for any subtle signature, any whisper of evidence that might suggest the presence of life beyond our own world. It aims to unravel the enigmatic processes that govern the formation of planets, the genesis of stars, and the grand, swirling architectures of galaxies. And, most spectacularly, it is designed to gaze across the vast expanse of the cosmos, focusing on celestial objects so incredibly distant that the light they emit has been journeying for nearly the entire age of the universe. In essence, this telescope was crafted to detect the nascent stars and primordial galaxies that emerged at the very threshold of our observable universe, objects born in the crucible of time itself. Already, the initial images it has transmitted back to us have begun to flow in, offering a tantalizing glimpse into its profound capabilities. For those who have followed this cosmic saga, the journey of this telescope from a visionary concept to a fully realized marvel has been a captivating narrative. Its initial inception dates back to the 1990s, with an original projection of a more modest billion-dollar budget and a launch target set for 2007. However, like many ambitious endeavors at the frontier of science, it encountered a series of formidable setbacks and protracted delays, pushing its launch date further and further into the future. It wasn't until December 2021 that it finally lifted off, embarking on a meticulous months-long process of unfurling itself, powering up its intricate systems, and rigorously testing its sophisticated hardware in the profound silence of space. This magnificent machine, weighing an impressive 500 kilograms, boasts a sunshield of truly immense proportions, stretching 14 by 21 meters, an area roughly equivalent to a tennis court. Its primary mirror, the colossal light-gathering surface, is an astounding 6 times larger in area than its predecessor's lens. This expansive surface allows it to capture a significantly greater number of photons from the most remote reaches of space, translating into images of astonishing crispness and detail. equipped with an array of advanced cameras and scientific instruments, it possesses the unique ability to observe across the entire infrared spectrum. This particular feature is absolutely crucial to its unprecedented mission. Due to the continuous, relentless expansion of the universe, the light emanating from the most distant cosmic sources has been stretched and elongated to such an extent that, regardless of its original wavelength, it now manifests predominantly as infrared light. Consequently, the only viable method for observing these ancient light sources is through the specialized lens of an infrared telescope. Moreover, infrared light exhibits a superior capacity to penetrate dense veils of cosmic dust and other obscuring debris, granting this telescope an extraordinary advantage, enabling it to glimpse objects that remain entirely hidden from the view of other telescopes. We often find ourselves comparing this new observatory with another iconic space telescope, a predecessor that has revolutionized our understanding of the cosmos for decades. This is largely because the newer telescope was, in its initial conception, envisioned as a successor to the older one. However, given their subtly divergent fields of view, the older telescope primarily operating within the visible light spectrum, while the newer one functions almost exclusively in the infrared and cannot perceive certain visible light wavelengths at all, it is more accurate to consider them complementary instruments rather than rivals. Together, they form a formidable duo, each expanding our comprehension of the universe in unique and invaluable ways. But our purpose tonight is to witness firsthand the extraordinary capabilities of this new telescope, beginning our journey within the familiar confines of our own galaxy and gradually expanding our gaze outward, ever outward, towards the very edge of the knowable universe. Prepare yourselves, for you are in for some truly spectacular sights, visions that promise to stir a profound sense of wonder within us. Our initial destination on this incredible voyage is a region of space colloquially known as the Cosmic Cliffs. These majestic formations, officially cataloged as NGC 3324, are nestled within the vast expanse of the Carina Nebula, situated approximately 7,600 light-years away from our vantage point here on Earth. Imagine, if you will, the sheer, unimaginable distance this light has traversed to reach our instruments, a journey spanning millennia, carrying with it the ancient echoes of cosmic events from a time long before humanity walked the Earth. These towering peaks, which appear before us in such breathtaking detail, are not merely aesthetic wonders, they are structures of truly colossal scale. Each cliff rises to immense heights, roughly 7 light-years tall. To put that into perspective, consider the distance light travels in an entire year. That is the measure of these celestial behemoths. And what we are privileged to witness here is but a fraction, a mere glimpse, of the nebula's grand totality. The Carina Nebula itself is an overwhelmingly larger entity, possessing a vast, hollowed-out central region. Within this central void, the powerful stellar winds, gushing forth from massive, luminous stars, have systematically swept away all the surrounding dust and gas, creating an expansive, cleared-out bubble. What we are observing in these stunning images, therefore, is the dramatic, illuminated edge of this enormous, sculpted cavity, a boundary where the turbulent forces of creation meet the profound emptiness carved by stellar might. Scientists hold a particular, deep fascination for this specific region of space, and for a very compelling reason, it offers invaluable insights into the intricate, often mysterious processes governing the formation of stars. It is here, at these cosmic frontiers, that the relentless pressure of stellar winds acts as a cosmic sculptor, driving dust and matter together into dense, clumping agglomerations. These dense pockets of material, under the inexorable pull of their own gravity, begin to collapse, initiating the slow, majestic birth of new stars. This makes the cosmic cliffs a veritable stellar nursery, a fertile ground where the raw ingredients of the universe are transformed into brilliant, celestial jewels. However, despite our continuous, eager stargazing and the ever-advancing capabilities of our observatories, many profound mysteries still enshroud this fundamental process. How, precisely, do stars coalesce from these nebulous clouds? What are the distinct, observable stages of their embryonic development? These questions have long puzzled astronomers, proving exceptionally difficult to answer with definitive clarity. A significant part of this challenge lies with the very dust that is so essential to the star-forming process. While indispensable for gathering the necessary mass, this same dust also acts as an impenetrable shroud, wrapping around the nascent stars like a thick, protective cocoon. This obscuring veil prevents us from clearly observing the intricate details of what transpires within, precisely at those critical moments when stars are truly taking shape, moments we most ardently wish to witness. This is where the new, powerful space telescope truly excels, transforming our observational capabilities. Not only do its images deliver an unprecedented level of detail compared to those captured by its predecessors, but critically, thanks to its sophisticated mid-infrared instrument, or MIRI, we can effectively peel back these dense, dusty layers. We can gaze directly into the heart of these stellar cocoons, discerning what lies hidden within. The clarity of these infrared images is truly remarkable, offering a window into processes previously obscured. This newfound ability will undoubtedly furnish scientists with a wealth of invaluable data on the mechanics of star formation, providing material for study and contemplation for many years, perhaps even decades to come. It's a leap in understanding, moving from inference to direct observation, allowing us to witness the universe's grand creative acts with an intimacy never before possible. From the vibrant, swirling spectacle of stellar genesis, we now turn our gaze to a different, yet equally profound, chapter in the life cycle of stars, their eventual demise. For this next stop on our cosmic tour, the telescope shifts its focus, bringing us a little closer to home to an object known as NGC 3132, more commonly referred to as the Southern Ring Nebula. This particular celestial tableau offers a stark, beautiful contrast, revealing the serene, yet dramatic, final acts of aging stars. The images we observe of the Southern Ring Nebula are particularly illuminating. One, captured by the telescope's near-infrared camera, presents a specific view, while another, taken by the mid-infrared instrument, provides a complementary perspective, allowing us to delve even deeper into its structure. This object is classified as a planetary nebula, though this term, as early astronomers discovered, is somewhat of a misnomer. While many nebulas are indeed the bustling birthplaces of stars, a planetary nebula, paradoxically, is not where planets are formed. The nomenclature stems from an unhelpful convention adopted by early astronomers who, observing the often rounded, disk-like shapes of these nebulas through their less powerful telescopes, mistakenly thought they resembled distant planets. The name, despite the subsequent evolution of our scientific understanding, has persisted. Planetary nebulas, such as this stunning example, are formed during the twilight years of a star's existence, as it nears the end of its life cycle. In a final, dramatic flourish, the dying star expels its outer layers of dust and gas into the surrounding space, blasting them outwards into a magnificent, expanding shell. Understanding the precise chemical composition of this ejected dust is of immense scientific value. By meticulously analyzing the materials present in these cosmic exhalations, we gain crucial insights into the fundamental building blocks that populate the universe. This knowledge, in turn, helps us to comprehend what subsequent generations, or waves, of stars might be composed of, and how the chemical enrichment of the cosmos proceeds over vast cosmic timescales. Once again, the new telescope's extraordinary capacity to penetrate the layers of obscuring dust and peer into the heart of these phenomena proves invaluable. Its infrared vision allows us to strip away the veils that would otherwise hide these crucial details. When we compare these new images with those previously captured by other observatories, the leap in detail and clarity is immediately apparent and truly astonishing. This enhanced view has allowed scientists to make fascinating new discoveries. For instance, within this particular system, researchers have learned that a second, companion star has not yet undergone its own dramatic explosion. This implies that the formation of its own planetary nebula is still a future event, a cosmic spectacle yet to unfold. Furthermore, these remarkably detailed observations have provided a much clearer understanding of how the gravitational interactions between the two stars within the system actively stir and blend the nebula's ejected material. This cosmic dance creates intricate, mesmerizing patterns within the swirling dust, offering a dynamic visual record of the profound forces at play. It's a testament to the telescope's power, allowing us to move beyond static images to inferred dynamic processes, giving us a deeper appreciation for the complex interplay of gravity and matter in these beautiful, dying stellar systems. Having explored both the fiery birth and the graceful, expansive death of stars within the confines of our own galactic neighborhood, our journey now propels us further outward, beyond the familiar spiral arms of our home galaxy. If our desire is to witness the vibrant, prolific creation of stars on an even grander scale, then our next destination is perfectly chosen. Approximately 161,000 light-years away, a truly magnificent and energetic region awaits us, the Tarantula Nebula. Its evocative name immediately conjures images of a colossal spider, lurking menacingly within its intricate, silken cosmic web. Beyond its striking, otherworldly beauty, a visual spectacle that transcends mere scientific interest, this particular area holds profound significance for astronomers. It bears a remarkable resemblance to a pivotal period in the universe's ancient history, an epoch known as the Cosmic Noon. To our best current understanding, this era unfolded approximately 1 billion years after the universe itself burst into being. During this energetic period, star creation reached its absolute zenith, a time of unparalleled stellar proliferation. The conditions prevailing within the Tarantula Nebula today are thought to mirror, in many crucial respects, those that characterized the universe during that prolific cosmic noon. The new telescope, with its unparalleled sensitivity and infrared vision, has been able to pinpoint individual stars within the Tarantula Nebula that are merely in their nascent stages of existence, only just beginning to coalesce and ignite. This offers an unprecedented opportunity to study a period of time that is both ancient and intensely active, providing a living laboratory for understanding the universe's past. By observing these young, forming stars, we gain direct insight into the processes that shaped galaxies and filled the early cosmos with light. It is a truly fascinating and critical period to study, offering a tangible link to the universe's formative years. As our gaze continues to extend outward, pushing the boundaries of our vision even further into the cosmic abyss, we gradually lose the ability to resolve individual stars. Instead, our perspective shifts, and we begin to perceive structures on a truly galactic scale. Even at these immense distances, where entire galaxies become the fundamental units of observation, intricate and beautiful cosmic ballots are continually unfolding. Our next observation brings us to a remarkable formation known as Stephan's Quintet. This captivating arrangement comprises 5 galaxies, though it's important to note that one of them is not actually physically associated with the others, but merely appears to be in close proximity from our Earth-bound perspective. This iconic grouping gained a touch of popular fame from its appearance in a classic film, It's a Wonderful Life. Scientifically, It is widely theorized that 4 of these galaxies are destined, at some unimaginably distant future point, to collide. Indeed, 2 of them are already engaged in a slow, majestic, and utterly profound gravitational embrace, a process of merging that is actively underway. The new telescope's capabilities allow us to observe, with astonishing clarity, the brilliantly hot dust that is being violently ejected and churned as these 2 central galaxies relentlessly circle each other. The gravitational forces at play in this colossal dance are truly mind-bogglingly intense, warping space and matter on a scale almost beyond human comprehension. The energy released during these gravitational interactions is profound, a testament to the colossal power of celestial mechanics. It is a cosmic ballot, a slow motion collision that is truly only appreciable and comprehensible when viewed at these immense, galactic scales. This particular image of Stephan's quintet is not a single snapshot in time. Rather, it is a magnificent composition, painstakingly assembled from nearly 1,000 separate images captured by the new telescope. Scientists then meticulously stitched these individual observations together, resulting in a composite image of incredible resolution. This extraordinary detail allows us to discern minute features and intricate structures within the colliding galaxies, revealing the subtle nuances of their gravitational embrace. It is a testament to both the telescope's power and the dedication of the scientists who transform raw data into these breathtaking windows into the universe. Let us now cast our gaze even further, pushing the limits until even the formidable capabilities of this new telescope are strained to their utmost. We arrive at an image known as Webb's first deep field. This extraordinary photograph captures a minuscule patch of sky, an area so incredibly small that a single grain of sand, held at arm's length against the night sky, would be sufficient to completely obscure it from your view. At this unimaginable scale, individual stars are almost entirely absent from the image. They are simply too small and too distant to be resolved on their own. Instead, the vast majority of the luminous points you behold are, in fact, entire galaxies, each a sprawling island of billions of stars. Within this profound image, we begin to discern the subtle, yet powerful, effects of gravitational lensing. This phenomenon manifests as fish lens distortions where relatively nearer, massive objects, often clusters of galaxies, possess such immense gravitational fields that they bend and magnify the light emanating from objects lying far beyond them. This cosmic distortion acts like a colossal, natural lens, allowing us to glimpse galaxies that would otherwise be utterly invisible, stretching and amplifying their ancient light. Through this gravitational warp, we start to truly see the outermost edges of the universe, the very boundaries of the observable cosmos. Nestled within this deep field image is one of the oldest galaxies ever detected by human instruments. Its distance is so immense, so utterly staggering, that the light from its birth, originating almost at the very inception of the universe itself, has only just now reached us. To truly appreciate its significance, we need to zoom in, to focus our attention on a tiny, faint red dot. Do you see it? It is, admittedly, quite small, almost insignificant at first glance. Yet, this diminutive speck holds a universe of information. By carefully evaluating specific markers within the light emitted by this tiny, reddish galaxy, scientists are able to determine how significantly its light has been redshifted. This redshift is a crucial indicator of distance in cosmology. As the universe expands, light waves traveling through it are stretched, shifting towards the red end of the spectrum. The greater the redshift, the longer the light has been traveling, and thus, the further away the object. By comparing this observed redshift to the normal visible light from similar, closer sources, this tiny dot was determined to be an astonishing 13.1 billion light-years away. Given that the universe is currently estimated to be approximately 13.7 billion years old, this particular galaxy represents one of the earliest, most primordial galaxies that we are ever likely to observe, a direct window into the universe's nascent moments. One might, understandably, feel a touch of disappointment at the seemingly small and indistinct appearance of this incredibly ancient galaxy. However, there is significant room for hope and, indeed, for even greater awe. To truly grasp the future potential, let us compare this image with one captured by a previous space telescope of the very same region of the sky. The difference is immediately striking. The new telescope's image is undeniably crisper, clearer, and reveals a far greater abundance of detail, showcasing a multitude of additional objects previously unseen. But there is one absolutely vital distinction, a profound difference that speaks volumes about the future. The older telescope, to produce its image of this patch of sky, had to stare intently for a remarkable 10 days, patiently gathering every single photon of light it could detect from this faint region and painstakingly compiling them into a single, cohesive image. The new telescope, on the other hand, achieved its equally, if not more, detailed image in only half a day. This implies a revolutionary capability. If this new observatory can achieve such astonishing detail in merely 1/20th of the time, imagine the unparalleled clarity and depth of image it could produce if afforded a comparable amount of observation time. In other words, this tiny, seemingly insignificant red dot is almost certainly not the ultimate best that this new space telescope is capable of. Its full potential, to delve even deeper into the cosmic dawn, remains largely untapped. These initial images, these breathtaking glimpses into the universe's grand narrative, have undoubtedly provided us with a profound sense of the scientific breakthroughs that are now within our grasp, thanks to the extraordinary power of this new space telescope. But beyond the sheer scientific utility, they also serve as a poignant reminder of the sheer, ineffable beauty of the universe's countless sights. Images such as these have the power to genuinely astound and humble us. Regrettably, we must exercise a degree of patience to fully comprehend the full scope of discoveries that this new observatory holds in store for us. It has only recently completed its meticulous calibration phase, allowing its sensitive instruments to cool to their operational temperatures and ensuring that every component is functioning with perfect precision. Already, there is an intense, global competition among scientists, a veritable queue of researchers vying for precious observation time, each eager to utilize its unparalleled capabilities for their specific investigations. Over its anticipated lifespan of 5 to 10 years, every second of observation time will be hotly contested and strategically allocated. It is poised to investigate exoplanets, searching for telltale signs of atmospheres that might be hospitable to life, extending our quest for extraterrestrial existence beyond our solar system. It will continue to unveil the secrets of nebulas, tracing the intricate origins of stars and illuminating the processes of their creation. Furthermore, it will play a crucial role in helping us to discern the fundamental differences between ancient, mature galaxies, like our own, and the young, vibrant galaxies that coalesced and formed mere moments after the Big Bang. With such an extraordinarily powerful tool at our disposal, a technological marvel of this magnitude, who can truly predict what other astonishing discoveries await us? The universe, it seems, is ready to surrender its deepest secrets, one breathtaking image at a time. To step outside on a clear night and gaze upward into the glittering, immense darkness of space is, in itself, a special and deeply moving experience. Yet, this terrestrial view, however inspiring, ultimately fails to capture the true, majestic grandeur of space and the boundless wonders it contains. Light pollution from our cities, the subtle distortions introduced by Earth's atmosphere, and the inherent limitations of our own eyesight collectively prevent us from truly exploring the universe in its full glory and uncovering its most profound secrets. Thankfully, for many decades, another pioneering sentinel, a venerable space telescope, has orbited majestically approximately 550 kilometers above our planet. From this privileged vantage point, it has allowed us to transcend these earthly limitations, peering deep into the cosmos, fundamentally altering our understanding of astrophysics and profoundly shaping our knowledge of the universe. Simultaneously, it has consistently dazzled us with a stream of truly remarkable and aesthetically stunning images. Tonight, we will embark on a complimentary journey, looking through the venerable lens of this iconic telescope. Our voyage will span billions of light years as we explore and provide context to the furthest reaches of our own galaxy, and then venture far, far beyond, all the way to the most distant object ever sighted by this particular instrument. What wonders will we encounter along this expansive path? What unexpected marvels will this seasoned observer reveal to us? Our first encounter on this particular leg of our journey takes us approximately 800 light years away, where we are greeted by the ethereal vision of vast, iridescent blue wings stretching gracefully into the silent expanse of space. But what precisely is this magnificent spectacle? This is NGC 6302, more commonly known as the Butterfly Nebula, a celestial jewel nestled comfortably within the spiral arms of our Milky Way galaxy. The nebula's spectacular array of vivid blue and shimmering turquoise hues are, in fact, the glowing remnants of gas, once the outer layers of a star that has reached the end of its life. The distinctive, expansive wing-like shape beautifully showcases the immense journey this gas has undertaken over the last 200 years, traversing a staggering distance of over 2 light years from its stellar origin. Recent meticulous observations of the Butterfly Nebula have unveiled an unprecedented level of intricacy within the powerful gas jets and bubbles that are still erupting from the dying star at the nebula's very core. These dynamic ejections are responsible for the rapid and continuous changes in the nebula's wing-like morphology, a testament to its ongoing, active evolution. It is a living, breathing testament to the profound transformations that occur during a star's final moments. Traveling onward, deeper into the galactic tapestry, we arrive at a distance of approximately 8,000 light years from Earth, where we discover the brilliant star cluster Pismis 24. This cluster is a veritable treasure trove of remarkable celestial phenomena, a sight that immediately captivates the eye. First, your gaze is inevitably drawn to the glowing core of a massive emission nebula, rising up like a luminous, cosmic cloud. Then, you will notice the striking blue stars, shimmering and lingering both within and around the nebula itself. These particular stars owe their intense blue coloration to their extraordinarily high temperatures, far hotter than our own sun. This extreme heat is directly related to their immense mass, which is a primary determinant of a star's temperature. Blue stars typically possess at least 3 times the mass of our sun, sometimes significantly more. These colossal blue stars are instrumental in imparting Pismis 24 with its signature vibrant color and unique texture. Their intense ultraviolet radiation, a furious outflow of energy, causes the vast clouds of gas surrounding the cluster to heat up dramatically and churn, forming remarkable, turbulent bubbles. This energetic environment makes probing the region with observational instruments extremely challenging, as the intense radiation and dynamic gas obscure much of what lies within. For a period, one particular star within the Pismis cluster, designated Pismis 24-1, was believed to be the most massive star ever recorded, estimated at nearly 300 solar masses. However, subsequent, more refined observations now suggest that it is, in fact, a system of at least 3 stars, each individually weighing in at approximately 100 solar masses. While this revised estimate makes them significantly smaller than originally thought, they still rank among the largest and most luminous stars ever documented, cosmic titans in their own right. Pismis 24 is itself embedded within the larger diffuse nebula NGC 6357, a region aptly described as a cosmic nursery. This nebula is a bustling haven for numerous protostars, stellar embryos still shrouded and protected by dense, dark gases. Protostars represent the earliest, most formative stage of stellar evolution, a period when stars actively gather mass from their vast parent molecular cloud. Alongside these nascent stars, many young stars are also present, encased within expanding cocoons of gas, giving the entire nebula the impression of a vibrant, living organism, constantly evolving and bringing new celestial life into being. Our journey now takes us even further, an expansive leap across the void, as we venture a staggering 60,000 light-years away from our home. Here we encounter Palomar 12, a magnificent globular cluster of stars suspended in the profound stillness of deep space. This ancient, tightly bound spherical collection of stars lingers on the distant outskirts of the Milky Way's vast halo, a silent, glittering sentinel. What immediately sets Palomar 12 apart from its galactic brethren is the surprising fact that its stars are approximately 30% younger than the other globular clusters typically found within the Milky Way galaxy. What could be the secret behind their comparatively youthful age? The answer, as it turns out, is a cosmic abduction. Palomar 12 is not, in fact, indigenous to the Milky Way galaxy. Its true origin lies within the Sagittarius dwarf elliptical galaxy. Approximately 1.7 billion years ago, this stellar cluster was violently torn from its home galaxy by the powerful tidal interactions with the much larger, more massive Milky Way. Indeed, the Sagittarius dwarf elliptical galaxy itself is currently in the slow, inexorable process of being ripped apart and absorbed by our own galaxy, a testament to the overwhelming gravitational forces at play in galactic mergers. These tidal forces are not merely confined to the immediate surroundings of individual galaxies. When galaxies collide or pass in close proximity to one another, the results are truly striking, often leading to the creation of strange, distorted shapes or unique, transient phenomena, as vividly demonstrated by the remarkable story of Palomar 12, where clusters born in one galaxy ultimately find their enduring home within another. But our journey, our relentless push outward into the cosmic unknown, does not conclude here. The venerable space telescope allows us to perceive far, far greater distances, unraveling the universe's grand design. Let us continue our voyage, now hopping more swiftly between these incredible cosmic landmarks. We begin this next phase at a distance of 30 million light-years, where the telescope grants us a familiar view, yet from an entirely new and revelatory angle. This is the Sombrero Galaxy, presented to us as if seen precisely from its side. This unique perspective clearly reveals the characteristic flat, disk-like shape that is common to the vast majority of spiral galaxies, a view we don't typically encounter when observing them face-on. One might naturally ponder why this flattened morphology is the prevailing norm. After all, planets, moons, and even smaller celestial bodies, like meteors, tend to adopt spherical shapes due to the pervasive influence of gravity. Shouldn't all galaxies conform to this spherical ideal? The reason for the more common, flattened disk shape observed in galaxies lies in the fundamental dynamics of the universe. As previously mentioned, the cosmos is in a state of perpetual motion. The immense gravitational forces, primarily exerted by the supermassive black holes nestled at the centers of galaxies, cause these colossal systems to rotate. This rotation, governed by the principle of the conservation of angular momentum, leads to an outward spreading, flattened, disk-like configuration. The Sombrero Galaxy is particularly distinguished by its intensely bright, almost blindingly white core, a luminous heart from which distinct lanes of cosmic dust spiral gracefully outward. The most prominent of these dusty lanes linger elegantly at the galaxy's very rim, giving it its iconic and unmistakable sombrero-like appearance. It is a striking example of how the interplay of gravity, rotation, and cosmic dust sculpts these majestic island universes. Continuing our outward trajectory, we now travel to a distance of 65 million light-years, where we encounter the broad, ethereal elliptical galaxy NGC 152 DF2. As you observe this distant cosmic entity, do you notice anything particularly distinct or unusual about its appearance? You might have discerned its remarkably diffused texture, so spread out and tenuous, in fact, that the light from even more distant galaxies can be clearly seen shining through its seemingly ghostly form. This transparency lends the galaxy a supernatural, almost spectral quality. Yet, the most perplexing and strange revelation about this galaxy is the strong possibility that it is almost entirely devoid of dark matter. This discovery was truly groundbreaking, as it was the very first galaxy of its kind to exhibit such a profound absence of this mysterious, invisible substance that is thought to constitute the vast majority of matter in the universe. As for the precise reasons behind this baffling anomaly, we are not yet entirely sure, and it remains a profound enigma. Let us now venture even further, pushing the boundaries of our cosmic perspective. This time, our journey takes us just over 300 million light-years from Earth to a colossal aggregation of cosmic structures known as the Coma Cluster. This immense gathering comprises more than 1,000 galaxies, all intricately bound together by the inexorable force of gravity. The Coma Cluster also holds a significant place in the history of astrophysics, as it was one of the very first locations where scientists discovered compelling indications of the presence of dark matter, the elusive substance that continues to challenge our understanding of the universe. In the image before us, a truly staggering sight unfolds. Thousands upon thousands of intracluster globular clusters are visible. These are spherical groupings of stars, ancient and tightly packed. But what makes them particularly intriguing is that they are not gravitationally bound to any single galaxy within the cluster. Instead, they are bound to the Coma Cluster itself, floating freely within the vast intergalactic space, a testament to the sheer scale of the cluster's gravitational dominion. While this might seem an almost incomprehensibly vast distance, our journey is far from over. We can and indeed will travel even further. Our next destination lies over 9 billion light-years away, an object famously known as MESS J1149, or more commonly Icarus. For a time, this singular star held the distinction of being the furthest individual star ever detected in the observable universe. The light from Icarus has been traveling for such an immense duration that it appears to us as it did when the universe was only approximately 30% of its current age, a breathtaking glimpse into the cosmic past. To truly convey the staggering remoteness of Icarus, consider this: at the moment its light was captured in this image, Icarus was at least 100 times further away than the nearest known star, a solitary beacon across an unfathomable void. Yet, even this incredible distance does not mark the limit of our observational capabilities. We can journey even further, to distances that truly seem to defy comprehension. Our next cosmic landmark is an object nicknamed Arundel, officially designated WHL 137 LS. This remarkable star, situated within the Celsus cluster, emitted light that took an astonishing 12.9 billion years to reach our telescopes. However, due to the continuous, relentless expansion of the universe, the actual distance between Arundel and ourselves is now even greater, estimated to be a mind-boggling 28 billion light-years. We are, in essence, observing Arundel as it was nearly 13 billion years ago, a ghostly echo from the distant past. Arundel is suspected to be a truly colossal star, estimated to be 50 to 100 times the size of our Sun. Given its immense mass, it is destined to conclude its life in a spectacular supernova explosion, a cosmic firework display that, from our perspective, is expected to occur within a few million years. The name, Earendel, itself is a poetic choice, derived from an Old English term signifying morning star, or rising light. It also serves as a subtle homage to the character Earendel from the works of J.R.R. Tolkien, who journeyed through the sky bearing a jewel as bright as a star. Beyond its intriguing name and impressive size, Earendel also boasts an incredibly high effective surface temperature, estimated to be at least 20 Zalosen Kelvin, nearly 4 times hotter than our Sun. There is also a tantalizing, albeit small, possibility that Earendel is a population Aetheri star. If confirmed, this would mean it contains almost no elements heavier than hydrogen and helium, being one of the very first generation of stars, and would be far more luminous than an average star, a true cosmic pioneer. Our ability to perceive this incredibly distant star is made possible through a remarkable cosmic phenomenon known as gravitational lensing. In this instance, a massive cluster of galaxies, situated between Earendel and us, acts as a colossal natural lens. The immense gravitational field of this galaxy cluster warps and magnifies the light from the star, bending it around the cluster in just the right alignment. This cosmic alignment effectively creates a natural telescope, allowing our instruments to see Earendel far more clearly than would otherwise be possible. It's an extraordinary example of how the universe itself, through the distortion of space, time, can aid our exploration of its deepest mysteries. At these truly unbelievable distances, even the venerable space telescope we have been discussing, the one that has provided so many groundbreaking images, is reaching its absolute limits. But the persistent question remains, is there anything further, anything even more remote, that we can possibly discern on our journey to the most distant reaches of space? The answer is yes. There is one more object this telescope can reveal to us. This final, incredibly distant object is a redshift galaxy known as HD1. It holds the current distinction of being the earliest and most distant known object in the entire observable universe. While to our eyes it appears as little more than a faint, reddish dot, HD1 is, in fact, an astonishing 13.5 billion light-years away, or at least, that was its distance when the light we now see was first emitted. Taking into account the continuous expansion of the universe since that ancient time, it is estimated to now be at a mind-boggling distance of 33.4 billion light-years. While it lingers at the very threshold of our current perception, this faint red dot still offers some telling details. Its extremely luminous ultraviolet emissions strongly suggest that it could be a starburst galaxy, a cosmic powerhouse producing stars at an unparalleled and furious rate. Alternatively, it might be home to the enormous population of Aetheri stars, those hypothetical first-generation stars described moments ago, which would be far more luminous than the stars we are familiar with. However, these theories, and any others we might formulate, remain speculative. This is due to the incredibly minimal amount of photons, the tiny packets of light, that we are able to collect from such an extreme distance. All we know for certain, for now, is that something profoundly significant exists out there, an object whose light has traveled for 33.4 billion light-years, and for the moment, that is the furthest thing that we can possibly see with this particular instrument. To glean more information, to perhaps even peer further into the cosmic dawn, we will undoubtedly require the unparalleled capabilities of the new, more powerful infrared telescope, the one we began our journey with. But until that next chapter of discovery unfolds, let us remain profoundly thankful for the breathtaking sights this venerable telescope has already shown us, and for the incredible 33 billion light-year journey it has graciously allowed us to undertake. And what an absolutely magnificent journey it has been. Now, Let us shift our focus from the grand, cosmic distances of intergalactic space to a more intimate, yet equally mysterious, frontier within the confines of our own solar system. In the profound, frigid void that stretches far beyond the orbit of Neptune lies a vast and enigmatic region. Here, the ancient remnants of our solar system's tumultuous birth drift silently through the darkness, perfectly preserved by the deep, unyielding freeze of space. To reach this shadowy, distant expanse from our home on Earth, we must first journey past the familiar rocky planets, soaring beyond Mars, then navigating the swirling, colossal storms of the gas giants Jupiter and Saturn. Further still, we venture out beyond the ice giants, Uranus and Neptune, those pale blue behemoths of the outer solar system. It is only then that we finally arrive at our destination. Welcome to the Kuiper Belt. This immense ring of icy debris encircles our solar system like a frozen halo, a colossal, donut-shaped repository of primordial material. It is far more than just a scattered collection of distant, frozen rocks. It is a veritable time capsule, a pristine archive from 4.6 billion years ago, holding the untouched, fundamental building blocks of our cosmic neighborhood. Within its icy embrace, it is home to several intriguing dwarf planets and a multitude of mysterious objects that have consistently puzzled and captivated astronomers. Join us now as we explore the worlds that lurk in the profound shadows of our solar system, piecing together crucial clues about its ancient history, about the intricate processes of planetary formation, the sporadic activity of comets, and even the fundamental origins of life itself. Long before we possessed definitive proof of its existence, astronomers had for decades suspected that something substantial must reside beyond the orbit of Neptune. For many years, the beloved dwarf planet Pluto was believed to be an isolated, solitary object, a lone wanderer in the frigid expanse of the outer solar system. However, certain observational anomalies simply did not align with this singular notion. Pluto's relatively small size and its unusually eccentric, inclined orbit strongly suggested that it was not, in fact, alone. Rather, it hinted that Pluto might simply be one among a much larger population of yet to be discovered distant objects. This theoretical suspicion gained significant traction in 1951 when the astronomer Gerard Kuiper, for whom the belt is now named, predicted the existence of a vast ring of icy objects just beyond Neptune's orbit. Yet, without telescopes powerful enough to actually detect these faint, remote bodies, the idea remained purely theoretical for many decades, a tantalizing hypothesis awaiting technological validation. That crucial validation finally arrived in 1992, when astronomers David Jewett and Jane Liu made a groundbreaking discovery, the first confirmed Kuiper Belt object, designated 1992 QB1. It is worth noting that Pluto and its largest moon, Charon, were both discovered considerably earlier, Pluto in 1930 and Charon in 1978. However, it was only after the confirmation of 1992 QB1 that these iconic objects were definitively recognized and reclassified as integral components of the Kuiper Belt. Since that pivotal discovery in 1992, thousands more Kuiper Belt objects have been identified, steadily populating this distant, enigmatic region beyond Neptune. To truly grasp the immense scale and precise celestial positioning of the Kuiper Belt, let us imagine ourselves aboard a conceptual spaceship, embarking on a grand tour. We begin our journey from the searing heart of the Sun, steadily moving outward towards the distant, cold reaches of our solar system. As we progress on this simulated voyage, let us continually compare the Kuiper Belt to both the more widely recognized asteroid belt and the even more remote, less well-known Oort cloud, to fully appreciate its unique place in our cosmic neighborhood. Starting near the Sun, we swiftly zip past the inner, rocky planets, Mercury, Venus, Earth, and Mars. Between Mars and the colossal gas giant Jupiter, we encounter the asteroid belt. This is a thin, relatively spread, outring of rocky debris, composed of the leftover materials from the tumultuous period when our planets were first forming. The asteroid belt resides approximately 2.2 to 3.2 astronomical units away from the Sun and spans about 1 astronomical unit in width. As a helpful reminder, 1 astronomical unit, AU, is precisely equivalent to the average distance from the Sun to the Earth. The vast majority of known asteroids, ranging dramatically in size from the largest, Vesta, which measures a substantial 525 kilometers wide, a distance roughly equivalent to that from London to Belfast, down to minuscule objects barely tens of kilometers across, reside within this particular segment of our solar system. However, despite occupying such an expansive volume of space, the cumulative mass of all the asteroids in the entire belt, when combined, amounts to only about 3% of the mass of Earth's moon. It is a surprisingly sparse region, more vast emptiness than solid matter. Beyond the relatively sparse asteroid belt, our journey brings us face to face with the colossal gas and ice giants Jupiter, Saturn, Uranus, and Neptune. These are truly immense worlds, their swirling atmospheres and ring systems dominating the outer reaches of our solar system, each a spectacular entity in its own right. Finally, as we successfully traverse and pass beyond Neptune's orbit, which lies at a distance of 30 astronomical units from the Sun, we reach our ultimate destination, an even more remote, icy frontier, the Kuiper Belt. This vast, icy expanse begins at approximately 30 astronomical units and stretches outward to roughly 50 astronomical units from the Sun. It is a cosmic wilderness, home to an extraordinary array of intriguing objects. These range from ancient, frozen relics, pristine remnants from the earliest epochs of our solar system's formation, to a fascinating collection of dwarf planets. Among these dwarf planets, we find the iconic Pluto, along with Haumea, Eris, and Makemake, each a world of unique characteristics and enduring mystery. Beyond these larger bodies, countless other smaller objects, icy planetesimals and fragments, drift silently through the cold darkness. Like the asteroid belt, the Kuiper Belt is a repository of ancient debris, preserving materials from the nascent stages of our solar system's birth. In fact, the objects within the Kuiper Belt are considered to be some of the oldest surviving pieces of the primordial solar nebula, the colossal cloud of gas and dust, from which all the planets of our solar system originally coalesced. Thus, at some incredibly distant point in the past, these stray, icy fragments might have possessed the potential to gather together, to aggregate and form yet another large planetary body. However, the powerful, relentless gravitational influence of Neptune intervened, disrupting the orderly coalescence of these icy objects and forever preventing them from forming something new, a testament to the planet's dominant role in shaping the outer solar system. Unlike the asteroid belt, which is primarily composed of rocky material, the Kuiper Belt consists predominantly of frozen methane, ammonia, and water ice. This forms a thick, donut-shaped ring of icy debris, a colossal, primordial deep freeze. The Kuiper Belt is estimated to contain hundreds of thousands of large icy bodies, each exceeding 100 kilometers in diameter, and an astonishing trillion or more comets, not to mention countless smaller fragments and fine dust particles. The average distance separating these individual objects is so vast, so immense, that it can be incredibly difficult to truly conceptualize. Each of these objects, on average, is separated by distances ranging from 0.12 to 0.1 astronomical units. Imagine, if you will, the equivalent of 10 million kilometers between individual objects, drifting in near perfect silence within these dim, outer reaches of our solar system. These icy bodies, these cosmic time capsules, quietly preserve vital clues about the fundamental origins of planets and the enigmatic behavior of comets. But our understanding of this region does not end there. That was merely the main, densest region of the Kuiper Belt. Overlapping its outer edge is another distinct area, known as the scattered disk. This region extends even further, reaching out to nearly 1,000 astronomical units from the Sun, with some Kuiper belt objects found on highly eccentric orbits that stretch even farther beyond that. So, while the asteroid belt and the Kuiper belt share certain similarities, both being reservoirs of ancient solar system material, it becomes clear that one is vastly, almost unimaginably, more expansive than the other. And while we may have reached the perceived end of the Kuiper belt, there remains yet another, even more massive, spherical structure that entirely envelopes every other object and belt we have discussed so far. In a previous exploration, we delved into the mysteries of the Oort cloud, that colossal, spherical shell of orbiting icy debris that completely encircles our entire solar system. It is so jaw-droppingly distant, so incredibly far removed, that even our most powerful telescopes are currently unable to catch a direct glimpse of its elusive presence. So, how do these two immense structures, the Oort cloud and the Kuiper belt, fundamentally differ from one another? For one, the Kuiper belt is thousands of times closer to the Sun than the central region of the Oort cloud, which is theorized to stretch from a staggering 2,000 to an almost unimaginable 100,000 astronomical units from the Sun. Another significant distinction lies in their morphology. The Kuiper belt maintains its characteristic donut shape, a flattened ring, while the Oort cloud is spherical, like a gigantic, swirling bubble of countless icy fragments, completely encasing our solar system. However, one crucial characteristic these two distant structures do share is their role as the primary sources of those spectacular celestial phenomena we know as comets. The Oort cloud is the birthplace of many long-period comets, those that take thousands or even millions of years to orbit the Sun, while the Kuiper belt is where many short-period comets, with orbital periods of less than 200 years, are born. While the Kuiper belt today stands as one of the most massive and significant structures within our solar system, it represents only a small fraction of its original grandeur. In its primordial state, it probably contained an astonishing 7 to 10 times the mass of Earth. However, the dynamic, shifting orbits of the four colossal gas and ice planets, particularly Neptune, exerted powerful gravitational influences, causing the vast majority of that initial mass to be ejected into the wider, interstellar space. What remains today is no more than approximately 10% of Earth's mass. Not only that, but the Kuiper belt continues its slow, inexorable process of erosion. Objects within it occasionally collide, shattering into smaller fragments. The resulting dust is then gradually blown out of the solar system by the relentless solar wind. Sometimes, these collisions, or the powerful gravitational tug of Neptune, can nudge Kuiper belt objects onto new trajectories, sending them hurtling inwards towards the Sun, thereby creating the short-period comets that occasionally grace our inner solar system with their luminous tails. Over time, the Sun's radiation causes these comets to shed material, producing the spectacular, luminous tails that we observe from Earth. Several famous comets are known to originate from the Kuiper belt or its scattered disk. Among these is Halley's Comet, with its average orbital period of 76 Earth years, a regular visitor to our skies. Another notable example is Comet Shoemaker, Levy 9, which, in a truly spectacular and unprecedented event in 1994, fragmented and dramatically impacted Jupiter. This was the first ever observed collision between two solar system bodies. As we know, Jupiter, in its immense grandeur, survived the impact, but the scars of the collision were visibly etched onto its atmosphere, a truly spectacular sight visible even from Earth. You may also have recently heard news regarding a near-Earth asteroid designated 2024 Y4. While there exists a very small, almost negligible chance of this asteroid colliding with our Moon, and an even smaller chance of it impacting Earth itself, it's important to note that the short, period comets originating from the Kuiper Belt currently pose no immediate threat to our planet within the next century or more. In other words, there is no need for concern regarding these icy wanderers in the foreseeable future. Despite the Kuiper Belt being merely a small remnant of its former, more massive self, it continues to offer a nearly endless frontier of fascinating objects for us to explore and study. And unlike the distant Oort cloud, which remains entirely beyond the reach of our direct observation, we have, in fact, been to the Kuiper Belt. While the majority of our current knowledge about this distant region comes from sophisticated ground-based telescopes and the orbiting space telescope, a particular spacecraft stands alone as the only human-made object to have actually journeyed through its icy depths. NASA's New Horizons probe is that pioneering spacecraft. It performed a groundbreaking flyby of the dwarf planet Pluto in 2015, providing us with unprecedented, close-up images and data of this enigmatic world. Subsequently, in 2019, it conducted an even more distant flyby of a Kuiper Belt object initially designated 2014 MU69, which was later officially named Arrokoth, a name meaning ski, in the Native American Powhatan or Algonquian language. This flyby of Arrokoth was, in fact, the most distant flyby in the entire history of space exploration, taking place an astounding 1.5 billion kilometers beyond Pluto's orbit. The New Horizons spacecraft came within approximately 500 kilometers of Arrokoth's surface, providing truly spectacular, high-resolution observations. Even among the countless mysterious objects that populate the Kuiper Belt, Arrokoth managed to profoundly surprise the New Horizons team. Its incredibly strange and unique shape was unlike anything humanity had ever observed within our solar system. Arrokoth is a small, icy Kuiper Belt object, classified as a contact binary. This means it is composed of two distinct lobes that, at some point in its ancient history, gently merged into a single, cohesive body. Its peculiar shape has been famously described as resembling a flattened snowman, measuring approximately 35 kilometers long, 20 kilometers wide, and a mere 10 kilometers thick. One might initially think that there wouldn't be much to learn from such a relatively tiny object, especially one seemingly devoid of an atmosphere or diverse geology. However, what Arrokoth lacked in these more conventional features, it more than compensated for with its utterly unique structure. The bizarre, pancake, snowman morphology of this Kuiper Belt object has provided absolutely crucial insights into the fundamental processes by which the building blocks of planets, known as planetesimals, came together in the early solar system. It offers a direct window into how planets themselves may have initially formed. Arrokoth's shape also seemed to imply a counterintuitive gravitational field and rotational behavior, prompting several scientific papers published since the flyby. These studies have led to an almost undeniable truth regarding planetesimal formation, a truth that even the New Horizons team hadn't initially anticipated. Planetesimals, as a concept, represent the intermediary stage where smaller objects gently come together to create progressively larger bodies, which may eventually, through continued accretion, combine to form a full-fledged planet. Until the Arrokoth flyby, there were two primary, competing theories regarding this process. The first, known as hierarchical accretion, proposed that small objects would repeatedly crash into each other at high speeds, gradually building up larger structures. The second, local cloud collapse, suggested that nearby objects would slowly and gently come together due to their mutual gravitational attraction, thereby forming larger and larger bodies in a more sedate, low-velocity manner. Now, thanks to the groundbreaking Arrokoth flyby and the subsequent, extensive research into the object's geology, geophysics, composition, and formation, we can be fairly certain that the theory of local cloud collapse is indeed the correct one. The remarkably smooth surface of Arrokoth, coupled with a notable absence of fractures or stress marks that would typically result from high-speed impacts, strongly confirms that this cosmic snowman formed at very low speeds, a gentle coming together rather than a violent collision. A planetary scientist and lead for the New Horizons mission stated that the evidence was so compelling, so robust, that it had decisively solved a multi-decade debate about how planetesimals form. And, of course, thanks to New Horizons, we were also afforded an unparalleled view of the most famous Kuiper Belt object of all, Pluto. The spacecraft's flyby in 2015 allowed us to get up close and personal with this enigmatic dwarf planet like never before, capturing those truly stunning, iconic images. The mission meticulously collected observations of both Pluto and Charon, the dwarf planet's largest moon, and was also able to gather valuable data on Pluto's other, smaller satellites Nix, Hydra, Kerberos, and Styx. We have all, no doubt, seen the stunning photographs of Pluto's distinctive, heart-shaped surface region, also known as Tomball Regio. But did you know that this iconic heart-shaped feature is, in fact, an enormous glacier? The western lobe of the heart, aptly named Sputnik Planitia after Earth's first artificial satellite, Sputnik 1, is a vast nitrogen glacier. It stretches an astounding 1,000 kilometers wide and plunges to depths of up to 4 kilometers, making it undoubtedly the largest known glacier in the entire solar system. The eastern lobe of the heart derives its lighter coloration from nitrogen ice that is sublimated from Sputnik Planitia and subsequently redeposited as a thinner layer of ice. Not only did New Horizons provide us with these breathtaking images of Pluto, but the data it collected fundamentally transformed our understanding of this beloved dwarf planet. It revealed that Pluto is far more complex and geologically active than we had previously imagined, and it offered crucial clues to the enigmatic origin of its heart-shaped feature. The initial data led some scientists to theorize that Pluto's heart-shaped region could be explained by the presence of a subsurface water, ice ocean, actively influencing its geology. However, a more recent study, led by an astrophysicist from a prominent university, has revealed another, perhaps even more likely, culprit. The heart shape, according to this research, may have been caused by a low-velocity impact event that left a gigantic, elongated splatter across Pluto's surface, creating the distinctive western half of the heart shape. This impact, according to the theory, would have occurred at an oblique angle, meaning it was not a direct head-on collision. Imagine for a moment the physics of throwing a water balloon across dry pavement in much the same way you might skip a flat stone across the surface of a pond. When the balloon scrapes along the pavement at a shallow angle, it pops, leaving behind an elongated, stretched-out splat of water across the surface. This kind of angled, low-velocity impact is strikingly similar to how the western lobe of Pluto's heart feature may have been created, a dramatic yet gentle sculpting by a cosmic projectile. But it's not just Pluto that we were able to see up close and in such exquisite detail. The images returned of Pluto's largest moon, Charon, were equally incredible and revelatory. Can you discern the enormous, prominent equatorial tectonic belt stretching across its surface? The very existence of this massive geological feature strongly suggests the presence of a long-gone, ancient water, ice ocean beneath Charon's surface, a testament to a more geologically active past for this distant moon. So, what lies ahead in our ongoing quest to unravel the secrets of the Kuiper Belt and, by extension, to deepen our understanding of our entire solar system? The New Horizons spacecraft is projected to finally exit the Kuiper Belt sometime between 2028 and 2029, continuing its solitary journey into the vast, uncharted expanse of interstellar space. While there is currently no designated target for a further flyby, it remains a tantalizing possibility that space agencies might identify another suitable Kuiper Belt object for it to investigate. New, powerful tools, such as the advanced infrared telescope we discussed earlier, could play a pivotal role in this future exploration. Their enhanced capabilities could help us to further analyze the chemical composition of Kuiper belt objects from afar, offering new insights into their formation and evolution. And perhaps, in the more distant future, a dedicated robotic mission might even allow us the unprecedented opportunity to land on one of these mysterious, icy objects, or even to collect a pristine sample for a return mission back to Earth. Who truly knows what other profound secrets await discovery out there in this vast, frozen frontier? As our technology relentlessly advances, future missions will undoubtedly push deeper and deeper into the Kuiper belt, slowly revealing more of its long-held mysteries, one icy world at a time. In the year 1977, two extraordinary pioneers embarked on what would become one of the most epic and enduring feats of robotic exploration ever undertaken. Their audacious goal, to unravel the profound cosmic mysteries surrounding our solar system and, by extension, our unique place within it. These twin spacecraft not only provided humanity with some of the very first and most spectacular imagery of our solar system's distant outer planets and their enigmatic moons, but they continue, to this very day, to transmit incredible new information about our universe from the vast, cold reaches of interstellar space. Some 47 years and an astonishing 24 billion kilometers later, these two probes are far more than mere instruments and intricate circuitry. They stand as enduring symbols of humanity at its very best, endlessly curious, remarkably audacious, profoundly ambitious, and incredibly resilient. These probes did not merely capture dazzling photographs of our gas giants and their diverse moons. They captured the hearts and minds of generations of people back home on Earth. These are the intrepid machines that have journeyed the furthest that any human-made object has ever traveled. They are true trailblazers, groundbreakers, venturing into the unknown. It is their unique opportunity, and indeed their inherent peril, to travel beyond the current reach of humanity, to capture images of phenomena and landscapes we had never before seen up close, nor have we seen since. Reflecting on the mission's profound impact, one of the mission's project scientists remarked, "When I look back, I realize how little we actually knew about the solar system before these probes. We discovered things we didn't know were there to be discovered, time after time." So, are you curious to see what these intrepid explorers learned? Join us now as we delve into everything you might ever want to know about these legendary missions, from the ingenious design of the probes themselves, to their epic grand tour of the outer planets, and finally, to their impending, poignant conclusion. It is one of life's subtle ironies that it is not always the newest, most cutting-edge technology that is advancing our understanding most profoundly at the very edge of our solar system, but rather these remarkably old machines. They possess onboard computers with less memory than the tiny chip inside your car's key fob. To this very day, they are still utilizing 8-track magnetic tape technology, a relic from the 1970s, making them, in many cases, older than many of the individuals watching this very presentation. This is the inherent conundrum of deep space exploration. The vast distances and extraordinarily long travel times mean that technology, however advanced at its inception, can become antiquated long before it reaches its most ambitious targets. Of course, these two probes were not initially designed with the intention of traveling all the way to interstellar space. Their original mandate was a more modest 5-year mission to explore Jupiter and Saturn and their larger, most intriguing moons. This ambitious initial objective was made possible only by a rare, once every 176-year planetary alignment, a celestial confluence that dramatically reduced the energy and time required for such a journey. However, after successfully completing all of their primary objectives at Jupiter and Saturn. The mission team, with remarkable foresight and ingenuity, added flybys of Uranus and Neptune to the objectives of one of the probes. These extended objectives were also successfully accomplished. Following these triumphs, the space agency announced the commencement of the even more ambitious interstellar mission, with the overarching purpose of exploring the outer limits of the Sun's sphere of influence and venturing far beyond. This final, epic journey would take both probes off the ecliptic plane into unexplored regions of the solar system, such as the termination shock, and then through the denser and hotter heliosheath, before finally crossing the heliopause, the ultimate boundary marking the entrance into true interstellar space. But how did these incredible machines manage to accomplish so much, far exceeding the scope of their original mission parameters? It all comes down to that enduring, incredibly effective technology and a series of brilliant design choices. To put it simply, they were built different. Let's explore precisely how. We begin with one of the most consequential decisions made during their design, their unique fuel source. Each probe is equipped with a long-lasting radioisotope thermoelectric generator, or RTG. This remarkable device converts the heat generated by the natural radioactive decay of a plutonium-238 isotope into electrical power. Upon their launch, these generators were capable of producing approximately 157 watts of electrical power, roughly enough to power a laptop, and perhaps charge a mobile phone simultaneously. While this might not sound like an immense amount of power, it was more than sufficient for the probe's initial needs. Crucially, while the power output of a radioisotope generator is in constant, gradual decline, its strength halving approximately every 87.7 years, it was designed to provide enough sustained power to keep the essential systems on the probes running until at least the year 2025, a truly astonishing longevity. This long-term fuel capacity was by no means an accident. You see, when these probes launched in 1977, the space agency faced a truly unique and fleeting opportunity. The outer planets would soon align in that extraordinary, once-in-176-year configuration, an alignment that had last occurred during Napoleon's first reign. This rare celestial geometry would not only enable the probes to visit Uranus and Neptune with minimal course adjustments, but would also provide them with a crucial gravity assist from each of the four outer giants they encountered. This slingshot effect dramatically increased their effective velocity, propelling them far beyond what their own rocket propulsion alone could achieve. This concept of gravity assist was relatively novel at the time, having only been attempted previously on earlier missions to Jupiter and Saturn. However, this narrow launch window imposed a strict deadline on the space agency. There simply wasn't enough time to plan and fund separate follow-up missions, and the national legislature would not earmark sufficient funding for a longer, more expansive expedition like the Grand Tour that the space agency had initially proposed. So, what did the mission team do? They devised a series of ingenious engineering feats, meticulously optimizing the probes for a potentially much longer mission, fervently hoping that the necessary funding and scientific justification would eventually follow. Each of the probes is equipped with 11 sophisticated scientific instruments. Most of these instruments incorporate redundancies, or backup systems, in case of a machine failure, and can be toggled on and off to conserve precious power, to adjust their course and maintain their precise orientation in space. The probes are fitted with gyroscopes for stabilization, referencing instruments, and 16 hydrazine thrusters, including a full set of 8 backups. These backups, and remarkably effective ones at that, were absolutely key to the probe's extraordinary longevity. They proved to be vital when, after 37 years of operation, one of the probe's main thrusters finally ceased to function. Its backup thrusters, after 4 decades of idleness, were commanded to engage, and astonishingly, they worked perfectly, highlighting the exceptional foresight and robust engineering that went into their construction. The probes also feature custom-built onboard computers which, by today's standards, are undeniably antiquated, yet were cutting-edge technology in 1977. The probe's wide, angle and narrow, angle lens cameras, for instance, are controlled by a computer command subsystem, which incorporates fixed programs for critical functions like fault detection and correction routines. Another key to their enduring success lay in their sophisticated computer systems. Each probe had a computer known as the Attitude and Articulation Control Subsystem, or ACS, and no, despite the name, it does not scold the probes when they exhibit sassy attitude. Attitude, in this context, refers to the probe's precise orientation with respect to Earth. Without this crucial alignment, their high-gain antenna would be entirely unable to send or receive signals from the space agency's deep space network. This is of paramount importance, as the probe's transmitters possess only the modest wattage of a refrigerator light bulb. At such immense, interstellar distances, their radio signals become barely detectable whispers, faint echoes against the vast cosmic background. To communicate with the mission team back on Earth, and vice versa, the probe's antennas must be meticulously pointed directly towards Earth, and the deep space network must, in turn, know their exact position in space. Otherwise, they would be irrevocably lost like a needle in a colossal 287 billion kilometer haystack. Each of these spacecraft is equipped with a 3.7-meter antenna for real-time data transmission and an 8-track digital tape recorder capable of buffering 536 megabits of data for future transmission. This was enough capacity to store approximately 100 photographs. While this represented a monumental leap forward from earlier missions, which had no onboard data storage whatsoever, it is still a mere fraction of what the smartphone in your pocket can store today. Despite these apparent limitations, these digital tape recorders were built with an astonishing focus on durability. The company that manufactured them claimed that their units could process over 4,000 kilometers of magnetic tape without exhibiting any visible wear and tear. They were designed to withstand the harshest environments imaginable and undergo rigorous tests for conditions that had never before been encountered. Yet, remarkably, these recorders performed flawlessly, without data loss or machine failure, for decades, until they were finally taken offline to conserve power. Not bad for machines that predate the World Wide Web by a dozen years. Durability was a chief concern throughout the planning and construction phases of these missions. There were many unknowns inherent in a mission of such unprecedented magnitude. To reach Jupiter, both probes would have to safely traverse the asteroid belt. At the time, many scientists genuinely believed that this region would shred apart any spacecraft attempting to pass through it, a gauntlet of lethal projectiles. However, earlier missions had successfully navigated the asteroid belt, which emboldened the team to attempt the same feat. Yet, failure at this early stage would have spelled disaster, ending the mission before the probes had even reached their first primary target. Luckily, both probes made it through the asteroid belt entirely unscathed, and thanks to their pioneering journeys, we now know that it is, for the most part, predominantly empty space. Even with all these remarkable successes, and with the probes performing far better than their engineers could possibly have hoped for, as the two spacecraft journeyed through the immense void between the planets, there was still at least one more formidable hurdle to cross. What would be the fate of these delicate machines in the unimaginably cold temperatures of interstellar space? The space agency had installed multiple heaters to ensure the machinery remained operational. Nevertheless, as the probe's power output gradually waned over the decades, the agency had to systematically turn off some of these heaters to conserve precious energy. When the cosmic ray detector's heater was finally powered down a couple of years ago, its internal temperature plummeted by a staggering 70 degrees Celsius. Needless to say, dispatching a repair team 23 billion kilometers into space is simply not an option. Consequently, everyone expected the instrument to fail, to break down under such extreme conditions. But, astonishingly, it continued to run smoothly, a testament to the extraordinary resilience and engineering prowess embedded in these venerable machines. The very fact that the probes have continued to operate so well for over 45 years is a profound testament to their intrinsic durability and the brilliant engineering that went into their creation. But with all this incredible technology, what precisely did they see? Let us now rewind our journey, returning to the very beginning, and follow the astonishing path they blazed across our solar system. On August 20, 1977, the space agency launched one of the twin space probes from Cape Canaveral, Florida. Its companion, the other probe, followed 2 weeks later, launching on September 5. Even though both probes were ultimately bound for Jupiter, the first probe was set on a shorter, faster trajectory, so launching its second actually made strategic sense. It successfully overtook its sibling on December 15, 1977, and was the first to exit the asteroid belt. Together, this dynamic duo was poised to capture a dazzling parade of images that were, at the time, absolutely revolutionary and profoundly expanded our understanding. But rather than simply taking our word for it, let us now immerse ourselves in those very sights. Just 13 days after its launch, the first probe sent this remarkable photo back to Earth. It serves as a sentimental starting point for our epic journey, the first of tens of thousands of images it would transmit over the next 5 years. Taken from a distance of 11.6 million kilometers from Earth, it might evoke memories of the iconic Earthrise photo captured by the Apollo 11 crew from the Moon just 8 years prior. In this image, we can clearly discern our beautiful blue marble, Earth, with its moon lingering in the distant background. The profound beauty of this photograph is almost haunting, especially when we consider how far this probe has traveled and how much it has witnessed since that initial snapshot. But we have an immense distance yet to cover, so let us move onward. It would be almost 2 years before the first probe finally made its approach to its initial target, Jupiter. This is a remarkable feat, considering the colossal distance of 714 million kilometers separating Earth from the gas giant. The first probe arrived at Jupiter on March 5, 1979. It was traveling at an incredible speed of 17 kilometers per second, 2 kilometers per second faster than its sibling. Despite leaving Earth first, the second probe arrived 4 months later, on July 9, 1979. This difference in arrival times was due to the trajectory the first probe took, which allowed it to gain more speed relative to the Sun through a more efficient gravity assist. It is important to note that the first probe was not the very first spacecraft to encounter Jupiter. That distinction belongs to an earlier mission, which had reached Jupiter 7 years prior, in 1972. While that pioneering mission certainly provided valuable scientific insights, it did not quite capture the public's imagination in the same dramatic way. However, by transmitting stunning images like the one before us, the later probe certainly did. This is Jupiter in all its magnificent glory, a swirling tapestry of color and motion. It is almost difficult to accept that these are actual photographs, not elaborate paintings or computer-generated images. If you look closely, you can spot 2 of its prominent moons, Io on the left, a vibrant, yellowish sphere, and Europa, the beige, colored moon, on the right. We will return to these fascinating moons later in our journey. Fortunately for us, the first probe even recorded its approach to the great gas giant in a spectacular time-lapse sequence. It captured photographs at regular intervals, approximately every 10 hours, which corresponds to one full Jupiter day. This meticulous timing ensures that the planet is captured at the same point in its rotation across all the photos. The 66 individual photographs were then expertly spliced together to create this mesmerizing time-lapse movie, spanning the first probe's approach to Jupiter from January 6 to February 3, 1979, covering a staggering distance of 27 million kilometers. It's difficult to decide whether this sequence is more incredible or terrifying. But let us now get an even closer look and uncover what other surprises this colossal planet might be concealing. Something that immediately stunned scientists was the dynamic and complex nature of Jupiter's atmosphere. They had anticipated observing east, west, and west-east winds in Jupiter's various atmospheric zones, but what truly caught them by surprise was the sheer amount of turbulence, the towering plumes of gas, and the intense rotational movement, all of which are remarkably clear in this image. You can immediately perceive how incredibly dynamic and active Jupiter's atmosphere truly is. Scientists had already suspected that Jupiter's most notable characteristic, its great red spot, might be a massive, counter-clockwise rotating storm formation. Not only did the probe's data confirm this long-held suspicion, but it also revealed a surprising abundance of similar phenomena in other parts of the atmosphere. The prominent white spot visible just below the Great Red Spot is a prime example of these unexpected storms. It turns out that Jupiter's atmosphere is, in fact, littered with them, a chaotic, beautiful symphony of meteorological activity that we had no prior knowledge of. When we typically think of planetary rings, our minds almost instinctively conjure images of Saturn. However, thanks to earlier mission data, scientists had long suspected that Jupiter, too, might possess its own ring system. The probe's data not only definitively confirmed the existence of 4 Jovian rings, but it was also the first mission to successfully image them. This particular picture, captured as the probe began to depart Jupiter, beautifully highlights these rings, appearing as a glowing orange line subtly protruding from the planet's luminous disk. Before we leave Jupiter and continue our extraordinary journey, we did promise to revisit its fascinating moons, Io and Europa. Perhaps the single biggest shock and most profound discovery from this expedition was the undeniable evidence of intense volcanic activity on Jupiter's moon, Io. Prior to the probe's arrival, geologists had largely theorized that Io would be a heavily cratered, geologically inert body, much like our own moon. While they did indeed find circular markings on Io's surface, these did not appear to be impact craters. Instead, the distinct dark spots visible in the images clearly indicated the presence of active volcanic hotspots and vast, molten lava lakes. This particular photo vividly shows lava flow from less than 1 million years ago, which, in geological terms, is incredibly recent and was entirely unexpected. We now recognize Io as the most geologically active site in our entire solar system. At the time these images were captured, it must have been an absolutely incredible experience to witness Io mid-eruption. Imagine expecting to see a moon similar to Earth's, only to stumble upon a landscape alive with fiery, explosive volcanism. These spectacular blue explosions on Io's surface propelled material and gas an astonishing 100 kilometers into space. The volcanoes are unbelievably active, erupting relentlessly every few hours, treating the probe to several truly jaw-dropping photographs. The next moon outward from Io is Europa, and it could not be more profoundly different. Europa is an icy world, and the first probe was the first to reveal to us that its entire surface is covered by curious, intricate scratch markings. Scientists initially hypothesized these to be some type of complex ice fracture patterns etched onto Europa's frozen crust. It was also the probe's data that first strongly suggested the tantalizing possibility of a vast, swirling ocean of liquid water, lurking beneath Europa's thick. Today, we know of 95 moons orbiting Jupiter. However, prior to 1979, that number stood at a mere 13. The probe's mission discovered 3 entirely new satellites, Thebe, Metis, and Adraste, bringing the total count to 16 moons by the early 1980s. Sadly, we do not have any close-up pictures of these newly discovered moons from that initial 1979 mission, though they have been imaged by subsequent probes. The next significant stop on the Grand Tour was Saturn. After 21 months of solitary travel, the first probe arrived on its approach to the majestic ringed planet in November 1980, closely followed by its companion 9 months later, in August 1981. As mentioned before, when one thinks of rings, one invariably thinks of Saturn, so let us begin our exploration there. Prior to the mission, Saturn was believed to possess only 5 major rings. However, the first probe's observations revealed a far more intricate reality. These rings are, in fact, composed of hundreds, if not thousands, of incredibly thin ringlets, each a delicate, shimmering strand of ice and dust. This was the closest flyby any probe had undertaken of Saturn at that time, hence the extraordinary detail and the wealth of new scientific insights gleaned. The probe also discovered an entirely new ring, the G ring, and provided crucial, unprecedented details about the F ring, which had been discovered by an earlier mission just 1 year prior, in 1979. The first probe's images showed us that the F ring is not a simple, uniform structure, but is, in fact, kinked and appears to be multi-stranded in nature, a truly perplexing and beautiful configuration. It also identified 2 small, shepherd moons within the F ring, named Prometheus and Pandora. This was a momentous discovery, as it provided compelling confirmation for a long-standing scientific theory that shepherd moons do indeed exist around narrow rings, their gravitational influence acting to keep the ring material tightly confined and prevent it from dispersing. The probe also introduced us to some truly ghostly, enigmatic features on Saturn's B rings. These appear scattered around the rings in the photo, resembling broad spokes on a colossal wheel. While they might seem innocuous at first glance, these spokes actually caused quite a stir, a profound scientific debate within the scientific community for a considerable period. You see, up until 1980, it was widely believed that Saturn's rings were shaped and maintained exclusively by gravitational forces. This understanding was well established and generally accepted. However, these mysterious spokes completely defied that theory. Their very existence was inconsistent with conventional gravitational orbital mechanics. To this day, the precise cause of these spokes remains unknown, but the leading theory involves electrostatic repulsion, where very small dust particles are somehow separated from the main surface of the ring by electrical charges. Sadly, as much as the data from the probe taught us about Saturn's magnificent rings, it also delivered a more somber revelation: Saturn is slowly, inexorably losing its rings. The planet's powerful gravity is gradually pulling the ring particles inwards, effectively turning them into a kind of dusty rain of ice particles falling onto the planet itself. According to space agency estimates, this process could lead to Saturn's rings completely disappearing within approximately 300 million years, a fleeting cosmic blink in the grand scheme of geological time. The probe's journey to Saturn raised so many new questions, so many tantalizing mysteries, that a dedicated follow-up mission was mounted in the 1990s, specifically designed to exclusively study the ringed planet. This later probe, launched in 1997, orbited Saturn for an impressive 13 years, providing an unparalleled wealth of data. But we are not yet ready to leave Saturn's territory. The earlier probes provided some truly decisive breakthroughs regarding the planet's moons. We already knew of 14 moons orbiting Saturn, but these probes revealed 3 more, bringing the total number at the time up to 17 moons. Let us now delve into some of the remarkable insights we gained from two of Saturn's most intriguing satellites, Titan and Enceladus. An earlier pioneering probe was the first to capture images of Titan, Saturn's largest moon. The data it collected sparked immense interest among researchers, leading to the later probes being sent to conduct a more thorough follow-up investigation. These later probes discovered that Titan possesses a thick, dense, nitrogen-rich atmosphere, a truly unprecedented finding. It was the first and only encounter with such an atmosphere beyond our home planet, a world shrouded in a hazy, orange veil hinting at complex atmospheric processes. Enceladus also proved to be exceptionally quirky, a world full of unexpected surprises. Take a moment to examine this captivating photograph. Enceladus is visible in the distant background, a small, icy sphere, with the majestic rings of Saturn sweeping across the foreground. Now, it's quite tricky to discern, but that distant moon is actively erupting. Enceladus spews out an astonishing 300 kilograms of water vapor every second, propelling these plumes up to 10,000 kilometers above its surface, a height 20 times its own diameter. As it gracefully orbits Saturn, these frequent, powerful plumes of water vapor erupting from Enceladus leave behind a distinctive, donut-shaped cloud, which, in turn, feeds one of Saturn's icy rings. This phenomenon was initially suggested by the probe's data, but it wasn't until a later, dedicated mission flew closer that we could definitively confirm its truth. Further geological data and imaging from that subsequent mission revealed that Enceladus's terrains are an unexpected mosaic of old and new. The left side, appearing smooth and unblemished, represents the newer surface, while the right side, densely packed with impact craters, is significantly older. This stark contrast strongly suggests that Enceladus is a geologically very active moon, a characteristic it was not previously thought to possess before these groundbreaking observations. Before we chart our course towards the enigmatic, wonky world of Uranus, we must bid farewell to the first probe. After its close flyby of Titan and its intricate dance with Saturn's rings, its trajectory was gravitationally bent upward, propelling it out of the ecliptic plane, the general plane in which the planets orbit the Sun. From this point, the probe set a direct course for interstellar space, an immense journey into the cosmic unknown. Of course, it would take another 32 years before it would actually reach that ultimate destination. But there's no need to worry. Its companion probe, the second probe, executed a precise slingshot maneuver around Saturn, utilizing the giant planet's gravity to propel itself onward, first to Uranus and then to Neptune. These would be the first, and to this day, the only flybys of these distant ice giants in human history, an unparalleled achievement in exploration. 5 years after its arrival at Saturn, the second probe finally made its approach to Uranus in January 1986. At its closest point, the probe came within a mere 500 kilometers of Uranus's cloud tops, providing humanity with its first, ever close-up views of this enigmatic world. The probe's observations revealed a startling absence of visible cloud features in Uranus's atmosphere, a stark contrast to the dynamic, swirling atmospheres of Jupiter and Saturn. Uranus presented a serene, almost featureless cloud deck, challenging scientists' preconceptions about the atmospheric dynamics of gas giants. The false color image on the right, however, brings out the subtle differences in the atmosphere of the polar regions, which are dramatically tilted on a 98-degree axis. But it was another peculiar tilt that truly stunned the mission's scientists. It was previously unknown whether Uranus possessed a magnetic field at all. Yet, the probe's data unequivocally showed that not only does Uranus indeed have a magnetic field, but it is also astonishingly tilted at an incredible 59 degrees relative to its rotational axis. This means its magnetic and rotational poles are severely misaligned, a profound deviation from what was previously understood. Until then, it was widely believed that these poles were always closely aligned, as is the case here on Earth, where our magnetic and rotational poles are only shifted by a modest 12 degrees. The stark deviation found on Uranus defied conventional planetary magnetic field models and forced scientists to fundamentally rethink their assumptions about how these fields are generated within planets. One direct side effect of this extreme misalignment of poles is that as the planet rotates, its magnetosphere, the vast region of space carved out and dominated by its magnetic field, wobbles dramatically, much like a poorly thrown football. Scientists still struggle to accurately model this complex behavior, but it might visually resemble something akin to a chaotic, asymmetrical magnetic bubble. The second probe's meticulous observations also unveiled more intricate details about the already known rings of Uranus and, remarkably, led to the discovery of 2 additional ones. It was the first mission to capture images of these dark, subtle rings, including its outermost ring, clearly visible in this photograph. These rings are composed of incredibly fine dust particles, a delicate, ethereal structure. The probe also discovered 2 small shepherd moons orbiting one of the newly found rings, a phenomenon similar to its earlier findings with Saturn's F ring. Here, these tiny moons can be seen from a distance of 4 million kilometers in a photograph taken on January 21, 1986. This mission significantly expanded the known count of Uranian moons. Prior to the second probe's arrival, we only knew about 5 moons orbiting Uranus. The probe sent us the first, ever close-up images of these previously known moons, which we will examine in a moment, but it also discovered an astonishing 11 more moons, bringing the total to 16 moons at that time. These groundbreaking discoveries provided invaluable data on the sizes, compositions, and orbital characteristics of these newly found satellites. Today, the number of known moons orbiting Uranus stands at 27. Okay, let's return to Uranus's 5 original, or OG, moons. They all appear to be conglomerations of ice and rock bearing similarities to the moons of Saturn. Oberon and Umbriel, pictured here on January 24, 1986, are heavily riddled with impact craters. Their ancient, dark surfaces suggest little to no significant geological activity in their history. Titania, which orbits between those two and is the 4th furthest from Uranus, is marked by huge fault systems and deep canyons, indicating some degree of past geologic and likely tectonic activity. Ariel, on the other hand, possesses the brightest and quite possibly the youngest surface of all the Uranian moons. This photograph, taken from just 129,000 kilometers away, strongly suggests that Ariel underwent substantial geological activity, leading to the formation of numerous fault valleys and extensive flows of icy material at some point in its distant past. Miranda, the closest of the 5 original moons to Uranus, second only in proximity to Puck, a small, rocky satellite discovered by the probe in 1985, yielded the most surprising and perplexing findings. The probe flew by Miranda on January 24, 1986, at an incredibly close distance of just 30,000 kilometers. This diminutive moon, barely 470 kilometers in diameter, turned out to be a captivating puzzle of geological dynamism, its surface shaped by a volatile and complex history. The second probe identified clear traces of internal melting and sporadic upwelling of icy material, manifesting as extensive, canyon-like faults plunging to depths of up to 20 kilometers. The lunar canvas is further adorned with distinctive, oval, racetrack-shaped features etched across its surface like cosmic scratches. The probe also observed terrace regions, where a striking mosaic of old and young, bright and dark, and heavily and lightly cratered terrains coexist in a chaotic yet beautiful arrangement. The prominent chevron-like characteristic seen here strongly suggests that Miranda's original surface was violently pulled apart, and the fragments were then forcibly reaggregated back together, creating this patchwork appearance. 3 weeks later, On January 25, the second probe departed Uranus, capturing this wonderful goodbye shot from a distance of 1 million kilometers, as it set off on its final planetary target, Neptune. After 3 more years of relentless travel, speeding through the void at an astonishing 54 Zalosen kilometers per hour, Neptune finally came into view. The second probe approached the furthest planet in our solar system on August 25, 1989, just over 12 years since its launch from Earth. It produced the first close-up images humanity had ever received of the giant blue planet, passing only 5,000 kilometers above its north pole, the closest of any of its planetary flybys. Hydrogen was found to be the most common element in Neptune's atmosphere, although the high abundance of methane is what imparts the planet with its characteristic, deep blue appearance. The second probe measured extraordinary wind speeds in Neptune's atmosphere, with the equatorial winds blowing at speeds reaching almost 100 kilometers per hour. These remarkable speeds were yet another profound surprise, highlighting just how dynamic and ferocious Neptune's weather systems truly are, a stark contrast to the calm appearance of Uranus. Scientists also discovered a massive storm on Neptune, aptly named the Great Dark Spot. This turbulent storm appeared to be rotating counterclockwise, much like the Great Red Spot on Jupiter, and exhibited winds reaching up to an astonishing 400 kilometers per hour, the strongest ever recorded in the solar system. One analyst commented on these findings in 1989, stating, "Every day what you see is brand new, nobody's ever seen it." It's just an incredible feeling. There are changes going on constantly on Neptune that happen very, very fast. The second probe also imaged Neptune's rings for the very first time. Up until 1986, scientists suspected the planet might possess rings, but they couldn't be certain. Intriguingly, the spacecraft identified several partial ring structures, or ring arcs, within Neptune's ring system. These arcs raised significant questions about the mechanisms responsible for their formation and long-term stability, particularly since they consist mainly of incomplete and dusty rings, a unique configuration among the ringed planets. A trip to Neptune would, of course, not be complete without a quick stopover at its largest moon, Triton. Triton, the coldest known planetary body in the solar system, revealed a fractured, complex surface, complete with erupting geysers of nitrogen ice and a distinctive pinkish nitrogen ice cap covering its southern pole. Scientists also identified dark plumes rising from its surface, which could indicate the tantalizing possibility of active ice volcanoes. The second probe also discovered 6 entirely new moons orbiting Neptune, further expanding our knowledge of this distant system. As the second probe turned around to snap one last, poignant look at Neptune and Triton, it had officially completed its grand tour of the outer solar system. Neptune's immense gravity bent its path downward, out of the ecliptic plane. From this point, it continued its solitary voyage into interstellar space, much like its counterpart, the first probe, had done 9 years prior. Speaking of the first probe, let's check in on where it has ended up since we last considered it in 1980. 1 year after the second probe finished its observations of Neptune, the first probe was already approximately 6 billion kilometers away from Earth. In order to conserve vital power for the unimaginably long journey into interstellar space, scientists made the difficult decision to switch off its cameras forever. However, on the poignant advice of a renowned astronomer and science communicator, the team decided to turn the camera around for one final picture, a look back at home and how far humanity had come. And so, on February 14, 1990, the first probe captured the most remote selfie in history from a staggering 6 billion kilometers away. The result was the infamous pale blue dot photo. In the immortal words of the astronomer himself, "Look again at that dot. That's here. That's home. That's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. He continued, "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we've ever known." This profound sentiment resonates with as much power and relevance today as it did 33 years ago. But what came next? What did these intrepid probes see and do in the vast, uncharted territory of interstellar space? In 1981, the first probe successfully escaped the ecliptic, which is Earth's orbital plane around the Sun, heading 35 degrees to the north. The second probe later went under the ecliptic, heading 48 degrees to the south. However, this was merely the beginning of their true journeys into interstellar space. To reach that ultimate destination, the probes would first have to traverse the termination shock, a turbulent region where the hypersonic solar winds emanating from our Sun collide with fierce resistance from the interstellar wind, a boundary where the Sun's influence begins to wane. Beyond the termination shock, the probes would encounter the heliosheath, a denser and hotter region where the slowing solar winds pile up, creating a turbulent, frothy boundary. This would then be followed by the heliopause, the final, outermost boundary between the heliosphere, the vast bubble of solar wind and magnetic fields surrounding our Sun, and the true interstellar space beyond. But contrary to what one might intuitively believe, the beginning of the interstellar medium does not actually mark the definitive end of our solar system. Indeed, it will be another 300 years until the first probe finally reaches the Oort cloud, that vast, spherical region of billions of icy planetesimals that encircles our solar system like a colossal, diffuse bubble. And it will be an astonishing 30,000 years until it finally exits the Oort cloud, truly leaving our solar system forever. When the probes traveled through the heliosheath, they made an incredible, unexpected discovery. Because the Sun's magnetic field spins in opposite directions at its north and south poles, this differential rotation creates a subtle, undulating ripple where they meet, known as the heliospheric current sheet. This is somewhat analogous to the concentric rings created when a stone is dropped into still water. However, when this sheet reaches the termination shock, it compresses dramatically as if those ripples were hitting the edge of a cosmic swimming pool. The probes discovered that after the termination shock, these stacked up ripples form distinct magnetic bubbles. This groundbreaking finding implies that the boundary of the heliosheath is not as smooth and clearly defined as scientists had previously theorized. Instead, it is a fluctuating, magnetically bubbly environment. This unexpected, messy finding has prompted a complete revision of our theoretical models of the heliosheath, highlighting the invaluable role of direct observation in refining our understanding. On July 25, 2012, the first probe became the first human-made object to definitively leave the Sun's heliosphere and enter the vast, cold expanse of interstellar space. It was traveling at an incredible speed of 540 million kilometers per year, or 3.6 astronomical units annually. The distance at which the first probe crossed the heliopause was approximately 120 astronomical units from the Sun, which itself was a significant revelation. The precise location of the heliopause was previously unknown, with some early models placing it as close as Jupiter, and others suggesting it was much, much further away. Remember, the heliopause is the boundary where the sun's solar wind is effectively stopped by its collision with the interstellar medium, akin to the crashing of two powerful bodies of water against each other. The solar wind is a steady stream of charged particles, such as electrons, protons, and alpha particles, that emanate continuously from the sun's outer layer. The interstellar medium, by contrast, consists of charged particles, various gases, and cosmic dust, all left over from the Big Bang and other ancient supernova explosions. When these charged streams collide, they change course and form a region of equilibrium, which we call the heliopause boundary. At first, the space agency was not entirely certain if the first probe had truly crossed the heliopause and entered interstellar space, as theoretical models had predicted. The probe's plasma wave detector found a massive, unexpected increase in plasma density, an astonishing 80 times what it had registered in the outer heliosheath, and a significant spike in galactic cosmic rays. But something strange, something entirely unexpected, did not happen, leaving scientists baffled. After crossing the heliopause, the first probe detected no change in the ambient magnetic field. Why was this so surprising? Well, theoretical models had consistently assumed that the ambient magnetic orientation would undergo a distinct change in a region dominated by the magnetic fields of other stars. Yet, remarkably, the first probe detected no discernible change in the ambient magnetism. The space agency was so confused by this anomaly that they waited nearly a year before finally announcing that the first probe had, in fact, entered interstellar space. On November 5, 2018, the second probe, traveling at the slightly slower speed of 490 million kilometers, or 3.3 astronomical units, per year, joined its sibling in becoming the second human-made object to enter interstellar space. Its crossing also occurred approximately 120 astronomical units from the Sun, and, like the first probe 6 years earlier, it detected no change in the ambient magnetic field. But something else surprised scientists about this second crossing. You see, the Sun goes through distinct 11-year solar cycles, during which its activity waxes and wanes. The second probe's crossing occurred at a time when solar winds were peaking, when the Sun was at its most active. Models had predicted that the size of the heliosphere would fluctuate with the solar cycle, meaning it should have been expanding when the second probe made its crossing. Yet, the second probe crossed the heliopause at exactly the same distance the first probe had 6 years prior, meaning our models were, in this respect, incorrect. Like the magnetometer finding, this demonstrated the immense value of testing theoretical models with actual field data. We now suspect that the boundary between the heliosphere and the interstellar medium is much more twisted and filled with fluctuations than prior models had proposed. One leading idea is that our Sun emerged billions of years ago from a hot and heavily ionized region following the explosion of one or more supernovae, and that magnetic turbulence persists to this day near the heliopause. If this is the case, the probes will likely encounter a different magnetic orientation as they travel further away, but their instruments will probably be long dark by that time. After all, these venerable probes are already beginning to show signs of age and wear. In early May 2022, the first probe's signal suddenly became strange and incoherent. Imagine, for a moment, being a scientist working for the space agency. You arrive at your computer for the day and begin reviewing the first probe's telemetry data. This probe regularly transmits status updates about its systems, letting you know whether everything is functioning normally. It now takes 22 hours for a signal to reach Earth from the first probe, so communication is, understandably, a little slow between you and the spacecraft you are overseeing, more akin to sending letters than instant messages. However, on this particular day, something is clearly wrong. The information it has transmitted is gibberish, an unintelligible stream of data. Instead of precise readings explaining exactly what the first probe's thrusters are doing and what orientation it believes itself to be in, you receive long strings of zeros or repeating numbers like 377. The information simply does not make sense. It suggests that the probe is performing actions and pointing in directions that are physically impossible. You quickly double-check your computer. Yes, you did just receive a signal from the first probe, so its antenna must still be pointing towards you, exactly as it always has. It cannot be pointing in the strange directions it is claiming, or you would not be receiving any signal at all. And not only are you receiving the signal, but it's at the exact same strength, confirming that it has definitely not changed direction. Ping! Onto your computer comes the first probe's latest science data. Strangely enough, this data is entirely normal. While over the years the first probe has had to switch off 5 of its 11 scientific instruments, and a further 2 have stopped working due to general degradation, the remaining 4 continue to take accurate readings about the interstellar medium, magnetic fields, and cosmic rays. Nothing here is garbled in any way. You check the other systems. The first probe's power supplies are a little low, but that is to be expected. The plutonium oxide that fuels its 3 generators has a half-life of 87 years, and the first probe has been traveling for 45 years now. It's no wonder the efficiency has started to decline. In fact, experts believe that the first probe will not last past 2025, but that's still some time away and doesn't explain what is happening now. After checking its other systems, it is just one that is behaving strangely, the AACS, the Attitude Articulation and Control Subsystem. This computer is one of 3 on the first probe, and its crucial job, as we discussed, is to ensure the spacecraft's large, 3-meter antenna continues to point precisely towards Earth. This ACS has stopped sending coherent data. You lean back, puzzled. The situation is not as dire as it might first have seemed, but it is certainly troubling. It's akin to receiving mail from a postman who greets you every morning, only for him to suddenly start speaking an entirely different, unintelligible language one day. The packages he delivers are still the same, and they've arrived at the correct address. It's just that the words the man speaks make no sense to you anymore. To further compound the strangeness, the first probe itself doesn't seem to think anything is wrong at all. The spacecraft is equipped with emergency safe mode, settings that it can activate if it detects that anything is not working as it should. These typically involve powering down non-essential systems until scientists can diagnose and fix the problem. None of these safe modes have activated, so the first probe genuinely believes that all its systems are working exactly as they should be. The data is given, the scene is set. This was the perplexing question that the space agency's engineers faced in mid-2022. A single fault like this might not seem like a monumental problem, but it hints at something potentially deeper and more widespread within the probe's intricate systems. If that were true, it could spell the end of the entire mission. The first probe is by now an astounding 23.8 billion kilometers away from Earth. Any solution would have to be derived through careful deduction, alongside a painstaking series of questions and answers with the faulty spacecraft, each exchange taking 22 hours to complete. By meticulously evaluating the rest of the systems and finding them to be normal, the engineers could rule out some of the more unusual and speculative explanations. No, this was probably not the work of aliens attempting to interfere with the probe, although the space agency's scientists were, in fact, open to the idea of the probes, perhaps one day being picked up by alien life, as evidenced by the golden discs installed on each probe, filled with messages about humanity for extraterrestrial beings to read if they ever stumbled across them. Besides, This would seem like a rather strange and inefficient way for aliens to communicate with us. And no, the laws of physics had not suddenly broken down. The first probe had not entered a wormhole that was skewing its perceived location while somehow still managing to transmit a signal back to Earth. Given that the scientific data all appeared to be providing normal, coherent readouts, it was far more likely that the problem lay specifically with the AACS itself. For 4 long months, scientists and engineers gently prodded and examined the first probe, testing theory after theory, and diligently trying to devise a solution that would rectify the problem without causing any further, unintended damage in the process. They considered switching over to a backup system. It would not have been the first time they had started using a new computer on the first probe after an older one had ceased functioning. The first probe, after all, was built with numerous redundancies. This wasn't even the first AACS computer that had been utilized. A previous one had become defective some time ago. They also contemplated simply leaving things as they were. After all, the crucial science data was still being transmitted. Would it truly be the end of the world if the first probe simply carried on speaking in garbled messages? Perhaps this could become the new normal. Except, it implied that a deeper, underlying problem was being overlooked, a ticking time bomb within the probe's aged systems. Can you figure out what was going wrong? If you can, perhaps the space agency should consider hiring you. It turns out that, in the intense, radiation-filled environment of interstellar space, something had caused the first probe to unexpectedly decide to start using that older, previously broken AACS computer to send its telemetry data back to Earth. Because of the inherent faults in this older computer, the data had become corrupted, resulting in the strange, nonsensical numbers that the engineers were receiving. So, in actuality, the fix was relatively straightforward. All the space agency had to do to resolve the issue was to command the first probe to revert to using the correct, functional computer again. Once the first probe complied, the problem was resolved. Well, we say easy and resolved, but it still took a couple of months for the first probe to start behaving normally again. And even then, in November 2023, another of the probe's onboard computers, this time the flight data subsystem, experienced a similar problem, becoming unable to transmit usable science and engineering data back home. It took until June 2024 until that problem was fully resolved. The first probe is an old ship now, a venerable explorer nearing the end of its operational life. As it continues its solitary journey through the vastness of interstellar space, it may encounter more and more faults, more and more challenges to its aging systems. In July 2023, a routine series of commands sent to the second probe inadvertently caused the probe to orient its antenna 2 degrees away from Earth. This seemingly small divergence was, over the immense distances involved, enough that the space agency completely lost the ability to communicate with the second probe or receive any signals back from it. It was only through the extraordinary effort of sending out an interstellar shout from the Deep Space Network facility in Canberra, Australia, a powerful, focused radio signal that a command was able to be transmitted to the second probe, instructing it to reorient its antenna back towards Earth. The 37 hours of anxious waiting for that shout to arrive, and for the probe to signal back that it had successfully followed the command, must have been incredibly tense for the space agency personnel. The probe could have been lost forever. One way or another, it is an inevitable truth that these 2 pioneering probes will eventually cease transmitting data back to Earth, whether through an insurmountable error, a critical malfunction, or simply by finally running out of power. The end is unavoidable, and the curtain will eventually fall on this incredible, historic mission. But even then, these twin probes are merely beginning their truly cosmic journeys. In approximately 40,000 years, the first probe will likely drift towards a star in the constellation Camelopardalis. Meanwhile, the second probe will pass within 1.7 light years of the star Ross 248, and in an astonishing 296,000 years, it will pass within 4.3 light years of Sirius, one of the brightest stars in our night sky. These small, intrepid probes, testaments to human ingenuity and resilience, will likely outlast the Earth itself as they continue their solitary, silent wanderings across the vast expanse of the Milky Way galaxy. And if, by some extraordinary chance, they ever encounter intelligent life in one of the far reaches of our galaxy, they will serve as an enduring testament to humankind's audacious curiosity and remarkable persistence. Remember, as we discussed earlier, that each of these probes carries a message to the stars. These golden audiovisual discs, known as the Golden Record, contain a carefully curated collection of photographs of Earth and its many diverse life forms, the evocative sounds of whales and the cries of babies, music by revered composers and iconic musicians, and greetings in 55 different human languages. They would offer a distant stranger, an alien intelligence, a fleeting glimpse of who we are and what life on Earth is like. As for us, we must eventually bid a fond farewell to these old, familiar friends and continue our own lives here on Earth, ever hopeful. Hopefully, the mission of these probes will not be our last brush with the stars, but rather, only the very beginning of humanity's grand cosmic adventure. Is the universe truly inescapable? If we were to someday conquer the limitations of light speed and journey to the universe's furthest observable edge, what might we genuinely find? Would it simply be more space, an infinite expanse of planets and planetary systems stretching on forever? Or would we, in some mind-bending fashion, somehow come back to where we started, a cosmic loop? Amazingly, according to the insights of modern scientists, all of these possibilities are on the table. But which one is ultimately correct hinges entirely on the fundamental nature of that unseen, enveloping world all around us, the very fabric of space, time itself. Join us today as we continue our series exploring the unseen world of 4D space and delve into the possible answers to the profound question: what is the actual shape of the universe itself? But first, let us begin by contemplating the concept of infinity. You are likely already familiar with infinity in the realm of mathematics. It is the abstract concept of a number so incredibly vast that it cannot possibly be surpassed or beaten. Of course, no such singular number truly exists. For any number you could conceivably name, another number could always be conceived that is at least one greater than it. But in a way, that's precisely the point of infinity. There is always another number, another possibility. And when it comes to our universe, we have, so far, discovered no definitive edges. There may always be another star, another planet, another galaxy. The idea of an infinite universe is, admittedly, a little mind-boggling for us. We live our lives in a very finite world, a realm with clear edges and definitive endings. So, the notion that there might be literally infinite more planets out there, an endless cosmos, can be profoundly bewildering. However, as we have developed progressively more powerful telescopes and relentlessly pushed back the veil of darkness further and further at the very edges of what we can observe in our universe, what we are consistently finding is that even the seemingly darkest patches of the night sky are in fact teeming with countless stars and galaxies. So, increasingly, an infinite universe might be a reality that we are compelled to contemplate and accept. But it is crucial to understand that simply because the universe might be infinite, that does not necessarily imply that there are an infinite number of things within it. This may sound a little counterintuitive at first, but allow us to illustrate what we mean. Believe it or not, there are different kinds of infinity, and when it comes to our universe, Three distinct possible scenarios could be true: a flat universe, a spherical one, or a hyperbolic universe. Let us take a moment to explain each of these profound possibilities. In a flat universe, if we were to construct an imaginary grid to broadly represent the fabric of reality, everything would appear fairly standard and conventional. All the lines within this grid would either be perfectly parallel to each other or precisely perpendicular. An infinite universe of this particular variety would simply extend outward in all directions forever and ever, a boundless, straight expanse. This concept, while profound, is perhaps a little less dramatically engaging, so we won't dwell on it excessively. However, this model closely aligns with how we, for the most part, perceive the universe to be. All lines of direction appear straight to us. We can distinctly observe the planets and stars around us, and we typically notice no significant curving or warping of space on local scales. However, this is not the only way that the lines of reality can be drawn. Consider, for a moment, the mesmerizing image of a black hole. You might immediately notice the strange, distorted rings that appear to encircle its equator, as well as seemingly extending across its top and along its bottom. This visual phenomenon is, in a sense, an illusion. There are no actual physical rings across the top or bottom of the black hole itself. What you are actually observing is the equatorial ring, but from the opposite side of the black hole. Due to the black hole's incredibly powerful gravity, the light emanating from that far side, instead of simply bouncing off upwards or downwards into space, is profoundly curved towards us as the black hole's immense gravitational pull inexorably draws it in. You are, in effect, seeing the top and bottom of the ring simultaneously, as if the light has been bent around a colossal, invisible sphere. This bending of light by gravity is, in fact, an excellent example of our second kind of universe, a spherical universe. In a flat universe, all the lines that constitute reality are essentially straight. But what if we were to introduce a fundamental rule: all lines must, instead, curve towards each other? There is only one way such a universe could be geometrically drawn, and that is in the shape of a sphere. Imagine trying to draw two perfectly parallel lines on the surface of a sphere. You might begin well, but you would very quickly realize that your task is utterly impossible. All lines, if extended far enough, would inevitably converge towards each other, intersecting at least twice as they eventually returned back to their original starting point. What would a universe based on these kinds of curving lines truly look like? Essentially, rather than moving in the straight line you thought you were traveling in, you would actually be moving along a massive, subtle curve. It's a bit like those classic computer games where you travel off one side of the screen only to magically reappear from the opposite side. In a spherical universe, you could travel infinitely, but ultimately, you would only ever end up arriving back precisely where you started. With a powerful enough telescope, and if light were to suddenly travel a whole lot faster, it would theoretically be possible to look out into the cosmos and actually see the back of your own head, a truly mind-bending prospect. This kind of universe contains a finite amount of things, a finite volume of space and matter, but it appears infinite because you just keep encountering the same things over and over due to the closed, curved nature of space. Thanks to objects like black holes and other powerful, massive stars, we do indeed have compelling evidence that our reality sometimes exhibits a curved, spherical geometry, at least in the immediate vicinity of large concentrations of mass. The interior of a black hole's event horizon, for instance, is an example of this kind of infinite, yet bounded, space. No matter what path you attempt to take, you can never escape its gravitational embrace. However, let us now consider our third and final example, the hyperbolic universe. This particular model is perhaps the most challenging to visualize, but the underlying idea is relatively simple. Instead of having all lines remain parallel or move towards each other, in a hyperbolic universe, every line must, by its very nature, move away from every other line. Drawing this is inherently tricky because everything continuously gets wider, expanding exponentially. The only way you can effectively represent this is to either physically buckle your nice, flat two-dimensional disk until it becomes something like a saddle shape, or to mathematically warp what you are seeing as if looking through a distorted lens. In such a warped representation, all of the objects, for instance, might appear as squares, but they are squares that are obeying our rule that all their lines must be diverging away from each other. This leads to the very strange situation where you could theoretically have 5 squares all meeting up at a single corner, instead of the usual 3 that are geometrically possible in normal, flat 2D space. Alright, this may seem a little confusing. What, then, would it truly mean if space itself were hyperbolic? Well, let's consider what it is we are curving around. You might have noticed, when we discussed our spherical shape, that there must be something we are curving around, some inherent direction of curvature. That direction of curvature is intrinsically linked to time. Imagine, if you will, a series of timelines. We delved a little more deeply into the intricate interplay between space and time in a previous exploration, which we highly recommend you revisit for a more comprehensive understanding. But for now, just remember for this model that objects in time consistently move forward along their individual timelines in the direction we might metaphorically call up or towards the future. If they move left or right, they are moving through space, getting closer to or further away from each other. If we introduce a large mass into this model, it profoundly warps these timelines. Now, if you were a small object traveling along one of those arrows, and you got too close to that massive body, suddenly your path of travel no longer goes directly up, towards the future. Instead, it pulls you left or right, towards the mass itself. There are several profound reasons for this, rooted in the geometry of space, time, but the essential thing to recognize here is that your straight path towards the future is now inextricably pulled towards the planet. Consequently, you would have to actively accelerate away from it, just to stay on what you perceive as a straight path.